All right, let's get into it. Today, we are diving deep into the stunning, intricate world of fractals. And we're not just here to admire them. We're on a mission to crack a secret code, a brand new universal law that's been hiding inside their beautiful complexity all along.
You know, it's a question that's been bugging scientists forever. You look at something with infinite detail, like a coastline or a fractal, and it just seems like beautiful, random chaos. But what if it's not? What if there's a simple, elegant pattern buried under all that complexity?
So, to crack this code, we have to start at the beginning. Where do these incredible shapes even come from? Think of it like we're about to decode the actual DNA of geometry itself.
Okay, so at the absolute core of every single fractal is this process called complex iteration. And honestly, it's ridiculously simple. You just take one little math rule, and you repeat it over and over and over again. And from that one simple act of repetition, all this breathtaking, infinite complexity is born.
Now, this right here is the master recipe the researchers were working with. And listen, don't get hung up on the formula. You don't need to solve it. Just think of it like a recipe with a few key ingredients. The really cool part is that if you change just one of those ingredients, like that capital K right there, you can create a whole universe of completely different fractals.
So, with this recipe in hand, the real investigation could begin. The mission was to create a map of this fractal universe, to figure out which parts were stable, and to see if there were any hidden rules that govern them.
So, what is a fractal, really? Well, in this context, it's pretty straightforward. The actual shape you see is made up of all the points that, when you apply the recipe, basically stay put. They're contained. Everything else, all that empty space around it, those are the unstable points, the ones that just shoot off to infinity.
And this brings us right to the heart of the mystery. The researchers noticed that as they tweaked that K value in the recipe, as they turned it up, the stable area, the fractal itself, started to shrink. The big question was, how? Was it just collapsing randomly, unpredictably, or is there some kind of hidden law controlling it all?
And this shows you exactly what they were up against. Look here. When K is low, at 5, you've got this big, healthy-looking shape. Then they crank K up to 15, and you can see it's already getting smaller. By the time K hits 25, whoa, the whole thing has just collapsed. This is the mystery they had to solve.
So after painstakingly mapping all of this behavior, which seemed totally chaotic on the surface, it happened. They had their aha moment. They finally cracked the code.
It really just boils down to this classic idea. They were staring at what looked like infinite complexity, but the answer they found was actually beautiful and simple. They just had to learn how to look at the problem in a totally new way.
And here it is. This is the big reveal. The secret wasn't one law, but 3. It turns out that every single one of these fractals falls neatly into one of these 3 universal classes, and it all comes down to a tiny piece of the recipe that the researchers called a gate. Think of it like a valve. The way that valve behaves, if it stays open, if it closes nice and smoothly, or if it just slams shut, that one thing determines exactly how the fractal's area shrinks. It's a predictable, universal law.
The key takeaway here is this. They found a single number, the universality exponent, which they call gamma. This number is like a master key. If you know gamma, you know everything. You can predict with pinpoint accuracy just how fast the area of any fractal in that entire class is going to shrink. It's a true universal constant.
Okay, that's a pretty bold theory, right? But a theory is only as good as its proof. So the next step was obvious. They had to put these new universal laws to the test against cold, hard data from a whole bunch of different scientific fields.
And they didn't mess around. They didn't just test it on 1 or 2 little examples. No, they took 8 totally different functions from 6 completely independent areas of science to see if this thing was really universal.
All right, let's look at the proof. Here's the first test. This is for a system where the theory predicted an exponent of 4/3. On the left is the prediction from the theory. On the right is what they actually measured in the real world. I mean, come on, look at that. They're practically identical.
How identical are we talking? We're talking 99.86% accurate. That is just an absolutely stunning confirmation of the theory.
But maybe that was a fluke, right? Well, let's see. Here's a completely different system, one where the theory predicted an exponent of 1/2. And again, check it out. The theory's prediction and the real-world measurement line up almost perfectly.
The accuracy on this one, it's almost unbelievable. 99.99%. At this point, the evidence is just overwhelming. This universal law is the real deal.
So this new law didn't just explain how the area shrinks. It also started to unlock other secrets that were hidden deep inside the fractal's geometry, revealing these key moments in the life of the shape.
For instance, they could now pinpoint the exact moment, right around k equals 11, when a sharp point, a cusp, suddenly just appears on the fractal's edge. And they found this critical tipping point around k equals 25. It's a sharp phase transition, where the way the shape collapses suddenly switches from a slow, predictable decay to a catastrophic exponential freefall.
And this is what's so cool about science, isn't it? Discoveries like these cusps and tipping points, they don't just give you answers, they make you ask even more questions. It's that moment where a scientist looks at the results and just goes, huh, that's funny, that leads to the next big breakthrough.
Which really leaves us with one final, fascinating thought to chew on. If a single, elegant code can bring order to the infinite complexity of these mathematical worlds, it just makes you wonder, how many other simple, universal laws are out there, just hiding in plain sight, waiting for us to find them?